Hello friends, today we're going to talk about oxidation of alcohols. Just a note, if you hear any sounds, that's either my dog Rosie or my brother's dog Penny. They like to play and roughhouse and make a lot of sounds, so you might be hearing from them. So, we can start off by oxidizing a hydrocarbon into an alcohol, which we've shown before, specifically with alkenes. If you hydrate an alkene, that turns it into an alcohol. But after you have already done that, you can oxidize alcohols into further compounds. So what I'm going to start off with is just a continuum of oxidation showing increasing oxidation state as we go. So if we start off with hydrocarbons, specifically alkenes, we can then oxidize that into alcohols through the hydration process that we've talked about in the past. Then that can split off into two different branches. Alcohols can be further oxidized into alkanals, also known as aldehydes. Or alternately, they could be oxidized into alkanones, also known as ketones. Continuing further, if we further oxidize the alkanals, we can oxidize those into alkanoic acids, which hopefully sounds like carboxylic acids to you guys, based on the ending of that. And then very last thing we can do to that is we can oxidize that into carbon dioxide. I'm going to use a different color for this, but this is showing increasing oxidation state as we go farther and farther. So that means that hydrocarbons are the least oxidized or have the lowest oxidation state, and carbon dioxide is the most oxidized or has the highest oxidation state. And as we oxidize these, we get different functional groups. So we're starting off with just an alkene, then a hydroxyl group, then either an aldehyde group or a carbonyl group, then a carboxyl group, and then this doesn't really have a specific functional group name, but that's just carbon dioxide. There's only some specific oxidizing agents that you can use. The most common are potassium permanganate, and that's going to be in a basic solution. Or you could have potassium dichromate in an acidic solution. So it's really important to note the differences for that. Because potassium dichromate is in an acidic solution, it is often written, as something like H+ / Cr2O7 - 2, like that. So these two things are interchangeable. You could see them either way. You're probably mostly going to see it this way, though. So this is called acidified potassium dichromate. And this one is the most common. Also, you could just use, in addition to those two, you could just use oxygen from the air. And just a note, if you see this symbol over an arrow, like an arrow in a reaction, that indicates that there's some sort of oxidizing agent present. So that's just a short way to show that. So before we move on, I want you guys to think about what types of alcohols can be oxidized and what types cannot be oxidized. And to do that, we need to think back to our types of alcohols. So we have primary alcohols, secondary, and tertiary alcohols. And one of these are not able to be oxidized. And I just want you guys to think about that for a second. So, something we can do to test what type of alcohol a compound is, like let's say you just have the molecular formula, but you don't know what it looks like. You can use acidified potassium dichromate as a test to identify if something is a primary, secondary, or tertiary alcohol. So type of alcohol. So if you guessed that tertiary alcohols cannot be oxidized, you would be right. The main issue with that is just that because of their shape, because of this shape here with all those branches, it's just harder for a compound to get in to oxidize that further. Also, if I were to oxidize this further, I would need to put a double bond right there, which I just can't do because then that would be 1, 2, 3, 4, 5 bonds. So that just can't work. But for this one, like the secondary alcohol, if I oxidize that, I could get rid of this hydrogen there, and then I can oxidize that further. So tertiary alcohols cannot be oxidized any further than they already are because that would be making too many bonds, and it's just kind of physically difficult to get in there with all those branches. So that means that if you put acidified potassium dichromate into a solution of some unknown alcohol type, if the alcohol is oxidized, that means it is either primary or secondary. If it is not oxidized, that means it is a tertiary alcohol. And remember that these symbols mean primary, secondary, and tertiary. So, when this starts off, it starts off as a bright orange color, and it has to be heated up, but after the reaction, it goes from orange to green. So that would be a clue that you have a reaction occurring. So if you had a solution of alcohols and you added acidified potassium dichromate and your solution turned green, you would know that you have primary or secondary alcohols present. So we're next going to talk about oxidizing our different types of alcohols. So to oxidize a primary alcohol into a carboxylic acid, it takes 2 steps. So first, you have to oxidize it into an aldehyde, and then from the aldehyde, you can oxidize that into a carboxylic acid. So let's see what that looks like. So first step, as I said, we have our alcohol to our aldehyde. So in this case, we're going to have ethanol being oxidized into ethanal. And in this case, we're using potassium dichromate. And then that little triangle just means that we're heating it up. That then produces ethanal, which is an aldehyde, and water as well, because what we're doing is we're taking off one of these hydrogens here and that hydrogen and turning it into water. So I will highlight that. Actually, we're taking off those 2 things to form that there. And then our oxygen from potassium dichromate is added on there. Our second step takes our aldehyde and turns it into a carboxylic acid. So we'll start off with ethanal again. And we'll add another round of potassium dichromate and heat. And then we produce ethanoic acid. And remember, I just chose to do potassium dichromate here. You could have, if you wanted, just said this symbol here and combine it with oxygen from the air. It's up to you. I just chose to do potassium dichromate. And then, so these are theoretically reversible if you were to take a reducing agent, which instead of showing this symbol, you just do an R in brackets. You can force it to go back. Of course, you'd have to add in heat, but it is theoretically possible to do that. Let's say I'm oxidizing ethanol again. If I want to just end up with ethanal, I can distill the products. So what that means is I would boil whatever products, and ethanal would evaporate first before ethanol does, because ethanal has a lower boiling point. So I could boil it off and then collect the vapors and then condense it down into a liquid form, which is what is done a lot of times in organic chemistry. If I instead wanted to make sure I get lots of carboxylic acids, I could then just make sure to expose ethanol to an oxidizing agent for a long time, and then heat it as well. It's called heating under reflux. So the way that works, let me see if I can show you on my computer. This is called a reflux setup. So what you do is you put your solution in this round bottom flask here. And then this is in a water bath or somehow connected to a heater, essentially. That boils. A lot of times that also spins just to stir things around. The vapors are then, like, these are connected here. So the vapors travel up into this tube here, where they then can kind of flow down into this tube here. Unfortunately, I can't remember what that's called, but it's a double layered tube. So the inside layer is where your product goes through. The outside layer has cold water flowing into it, but the water does not ever get into this part of the tube. It always stays on the outside. So it's like you have a tube within a tube type of a thing. By cooling this tube here, you force your product to condense into a liquid form, and then it just drops out here into some sort of collection vessel, whether that be a beaker or another round bottom flask or whatever. And if you wanted, you could do this several times to make sure you get a really pure product. So if you ever, like in college, for example, if you take organic chemistry, I guarantee you're going to see this setup. You're going to be very familiar with it. I think we might have some of this glassware at school. I think we only have one set though, and it's very small. So whenever we go back to school, I can show you what that looks like, but this is the basic setup here. And you can do this with things other than just aldehydes. Like you could distill a carboxylic acid, or, well, actually that would be hard. But that's how, commercially, how these things are sort of purified. That's a really good purification method. If you wanted, here, let me show you. To reflux a carboxylic acid, you do basically the same thing. This would be your end product after you've exposed your alcohol to acidified potassium dichromate for a while. It would be in here, it boils, then your product condenses in here, but this time it just falls back into here because it would have a higher boiling point than your alcohol or whatever else. So you'd be able to just condense it back in there. All right, so this is primary alcohols. For secondary alcohols, I'm gonna give myself a flap on this paper. I'm gonna just tape it like this and then fold it over, just because there's not enough space to write about secondary alcohols here. So secondary alcohols are oxidized to alkanones, which hopefully the ending "-one" tells you that that's related to a ketone. So let's, for our example, we have our alcohol going to a ketone. And this, well, actually, let's specify secondary alcohol. I'm going to specify there that's a primary alcohol. Our secondary alcohol going to a ketone is just a one-step process in this case. So for our example, let's look at 2-propanol. Then we're going to have our oxidizing agent. In this case, I'm just going to stick with potassium dichromate and heat. Then we end up with propanone. And just water left over. I'm not too worried about mechanisms for this, because if you look at this reaction pathway summary sheet, the only mechanisms that you need to know are alkane to halogenoalkane and halogenoalkane to alcohol. So you do not need to know the mechanism for alcohol to ketone or alcohol to aldehyde and then aldehyde to carboxylic acid. You just need to know the conditions that you need. So we're going to work on this later, but what you would do is just write the conditions needed above each of the arrows here. For the mechanism, I'm thinking we'll probably write that on the back of this paper, but that's a preview of what's to come later. So the reason why secondary alcohols can only be oxidized to a ketone is because they only have one hydrogen connected to this carbon right here. If they had two hydrogens, like we did in our primary alcohols, then we would be able to keep one of those hydrogens and turn our thing into a aldehyde. But that's not possible in this case, so that's why. So that hydrogen and that OH go into H2O here. And then, just like I was saying before, that's different compared to this because this has two hydrogens there. So if we had, for example, 2-propanol, that would oxidize to propanone, and so on and so forth. And you will always produce whatever ketone and water at the end. You could think of oxidation of secondary, or oxidation of any alcohol really, as a dehydration because you are always producing water as one of the byproducts. Tertiary alcohols can't be oxidized. And that, like we said before, is one, because it's just kind of physically blocked, but also because there is no hydrogen that can be removed to form some sort of a carbonyl group. So those are R's, by the way. No hydrogen to be removed. Therefore, no carbonyl group can be formed. Just checking my notes really quick. Let's talk about esterification really quickly. So we have the word ester here, and ification means that we are making an ester. The way that that works is you have an alcohol plus a carboxylic acid. Oops. Unfortunately, I left all my erasable pens at school, so that makes me sad. So we have an alcohol plus carboxylic acid gives us an ester and water. So this is another example of a dehydration, essentially. So let's look at ethanoic acid, so let's do this in order here. Let's do propanol instead. So we have propanoic acid plus propanol, sorry about that, plus ethanoic acid. When we combine these two together, what happens is we take the hydrogen off of propanol and the OH off of ethanoic acid. And then what we do is we just connect this oxygen right here. We connect this to that carbon right there. So what we form is called propyl ethanoate, but what it looks like is this. And then we also form water. Oh, let's write the name. Propyl ethanoate. Notice when we're writing the name, oh, sorry, you can't say that. When we're writing the name of propyl ethanoate, it goes alcohol, name, minus all, adding ill. Then carboxylic acid minus enoic acid plus NO8. So that's saying, what this is saying is we have propanol plus ethanoic acid forming propyl ethanoate, and then water at the end. So we can do another example of that. And this was actually the lab that Mrs. Slater and I really wanted to do with you guys, but now I'm not sure there's time. So another example. So our alcohol in this case is ethanol, and our carboxylic acid is called butyric acid. And this was the carboxylic acid that smelled like rotten Parmesan cheese when we were doing it I can't remember when that was, but at least a month ago. The thing that stunk so bad was butyric acid. So prefix eth means we have 2 carbons, and then enol means we have a hydroxyl group. Then bute means we have 4 carbons. And then the ic acid means that we have a carboxylic acid on one end. So I'm going to draw that like